Welcome back, everyone. It's good to see you guys again this morning. Another week full. It's our second full week. A few announcements. The readings for this week have moved around slightly. I realized that the order I was introducing things didn't quite match up, so those have moved around a little bit. The schedules were updated on the syllabus and in the files. Additionally, I posted the project on Saturday. Yeah, we need to form groups of 3 to 5 for that. So if you've got people, form those groups and send me an email with everyone sort of listed. And if you don't have a group, or you don't have people that you want, if you're struggling to find a group, there's a forum on Piazza specifically for finding teammates. If you're still struggling, let me know, and I'll assign anyone who doesn't have a group to groups, and then we can get to work on the project. Homework 2 is due tonight. I have office hours 4 to 6, and then homework 3 is due on Friday. And I'm considering moving my office hours from Saturday to Friday just to be in line with the homework being due. I think that's it for announcements. Yeah, so let's get into the content. So today we're going to talk about standard equality form of LPs, and that is useful to us because in the last class or so we discussed some methods for exploring solutions to systems of linear equations. Specifically, we talked about basic solutions to systems of linear equations. And the disconnect was sort of that our LPs are not systems of equations, they're systems of inequalities. And so we have to develop a way to sort of redefine, re-express our polyhedral feasible regions as systems of linear equations to use our sort of basic solution technique. So that's what standard equality form is, and that's what we're going to talk about today. And this is especially useful because basic solutions to our standard equality form will correspond to extreme points of our polyhedral feasible region, or at least potential extreme points. And I'll make that clear what that means exactly when we get there. So let's jump right in with a little example. We're going to work backwards a bit. We're going to start with an equation, or to an equation and a non-negativity constraint. And what we're gonna do is we're going to project this system onto the x variable alone. We're going to project out the s variable. And I'll show you sort of what that means graphically here. Here we have that equation, 1/2 x plus s equals 5. And we've restricted it so that s is non-negative, s is positive. Right. So we could have, I guess the projection basically asks what values can x take? Right, so yeah. So we sort of don't care about s in this sort of projection idea. We only care about s in that it puts some restrictions on x. So it must be that x is on this line. xs is on this line. And s has to be greater than or equal to 0. So when s equals 0, we get x equals 10, right? We get this point. And if we pick any value of s that's bigger, we get some other value of x. In fact, we get this line going backwards. So x can take any value less than or equal to 10. And in fact, since there's no non-negativity on x in this example, it can go on to negative infinity. So graphically what we've done is we've taken this line and sort of dragged it down out of the S space and entirely onto X. And we're left with X less than or equal to 10. This is sort of the inverse of what we're going to do to put things in standard equality form. In general, well, so our LPs will typically have inequalities in them, like the right-hand side here. But we want them to be equations. So what we do is we add an extra variable, which sort of re-expresses our half space as a hyperplane in one greater dimension. And this works because when we project out that new slack variable, as we'll call it, we're left with our original inequality. So in general, an n-dimensional half space can be expressed as an n+1 dimensional hyperplane. So sort of in set notation, if we have a half space, then we can express it, then it's the same as this projection of this hyperplane. Remember, this is a hyperplane because it has an equality rather than an inequality. And it's important to remember our S non-negativity, because if that was a free variable, then suddenly this would not actually enforce the inequality. So if we could subtract S here, then we could sort of effectively increase the right-hand side of our constraint. So maybe what if I write it like this? A transpose X equals B minus S. Since S is non-negative, all we can do is effectively decrease our right-hand side value. It can't get any bigger than b, but it can get as small as we want it. Just like our inequality here, ax can't get any bigger than b, but it can be as small as we need it to be. Now if we have a greater than or equal to in our half space, then we instead subtract s, so that A transpose x equals b plus s. We can increase the right-hand side of our equation to match whatever value ax, whatever valid value A transpose x equals in our inequality. We can increase the right-hand side so that our left-hand side can be greater than or equal to b. Now just to reiterate why we do this, half spaces, polyhedras, polyhedrals, oh my goodness, I cannot pronounce things today. Polyhedra have many, many solutions, but we're only interested in the solutions that actually sort of ride on their defining hyperplanes, the hyperplanes that sort of define the barrier for a half space. So having systems of equations rather than inequalities lets us use linear algebra techniques to find solutions that are worth looking at. And while we don't want to explore the whole polyhedron necessarily, we don't want to lose information about what solutions are feasible. So let's look at a graphical example. This is I think the same example we used in the last class. And I'm going to go ahead and write these. I'm going to add in our slack variables to our inequalities and make them equations. So we subtract a slack variable for a greater than or equal to. We do the same and for a less than or equal to, we add a slack. So what if we have, let's just pick a solution out here in the middle. We're going to call this x bar, y bar. And our slack variable is going to represent sort of the distance between our solution and whatever constraint that slack variable is a part of. So let me draw in the other slack. Not 4, it's S3. Now the book, when they add in slack variables, they just continue using x's. I find that a little confusing. So I tend to write my slack variables as s's rather than x's. This will help when we get to the sections on duality, because slack variables plane, and sensitivity analysis, because being able to identify slack variables from true decision variables is important in those contexts. Yeah. So if we solve for S1, we get x bar 3y bar minus 6. Which is the distance in sort of quotation marks. It is a distance, but it's not necessarily the same unit of distance between different constraints. So that is the left-hand side minus the right-hand side of that constraint, right? In other words, S1 is the sort of the distance, the slack between the left-hand side and the right-hand side of our constraint. And we'll see that this pattern continues. Excuse me, minus 10. And S3 equals 4 minus y. So this one is slightly different just because the inequality is the other direction. Remember that slack variables are going to always be non-negative. So by our constraint, 4 should be greater than y. So 4 minus y is positive. Y minus 4 would be negative. So let's think about a slightly different solution. Let's pick this solution right here on this edge. That's not a color we can see. I already used yellow. I'm going to use red. Yeah, there we go. I'm going to pick this solution right here on the edge. Now remember that S1 is sort of the distance between our point and the blue constraint. Since our point is on the blue constraint, S1 equals 0. Excuse me. Similarly, if we're at an intersection of constraints, here we have S2 and S3 equals 0. And maybe this is piquing some remembrance for you. Remember, when we're finding basic solutions, we were picking some variables and setting them equal to 0. So we're going to formalize sort of how a basic that should give you a hint as to how a basic solution corresponds to an extreme point. And we'll sort of codify that a little better coming up. But first, in general, an n-dimensional polyhedron that has m constraints can be expressed as an n plus m dimensional system of m linear equations. So given sort of this polyhedron, we can add in the identity matrix times some slack vector to get a and the non-negativity on the slack to get, instead of a polyhedron, this is just a system of hyperplanes of linear equations. Now let me show you, well, yeah. So is anyone not following my sort of convoluted explanation of this process? Okay, so let me say just one more thing. This is an unbounded polyhedron, but it is an intersection of half spaces, so it is still a polyhedron. Like we had, and we added slack variables. It's the same thing we're doing here in a generalized sense. We're adding one slack variable to every constraint on that that defines that polyhedron. And naturally, we recall that not all of our LPs in their sort of natural, most legible format had less than or equal to. They could have had greater than or equal to, in which case we would have a negative 1s. But recall that we can multiply both sides by negative 1 and flip that inequality while keeping the constraint the same. So we'll do that sort of transformation coming up here in a second. First, I want to talk about I want to do a slightly higher dimensional example. We have the Soylent problem. We're going to turn this into standard equality form. We're going to change all of the inequalities to equations by adding slack variables. So this is a greater than or equal to. So what we want is to sort of be able to increase the right-hand side. So the left-hand side can be as big as it wants, but no smaller than 1500. But instead of putting our slack on the right-hand side, it's more useful to put it on the left. So we subtract it over, and we have a minus S1 equals 1500. And in the same sort of sense, here we have a less than or equal to. So we want to be able to decrease the right-hand side. But we want our slack variables on the left. In the same fashion, we get a minus x3 here to make that an equation. This is already an equation, so we don't need anything there. And then we need to include non-negativity for our new slack variables. And that's the basics. That's the fundamentals of standard equality form. That's the biggest thing you need to know to put an LP in standard equality form. Add a slack to the left-hand side for less than or equal to, subtract a slack for greater than or equal to, and then make everything an equation. So this is called standard equality form, as I've said a few times. And the aspects of standard equality are that all variables are non-negative. So that includes slack and decision variables. Every constraint that is not non-negativity, constraints are equalities or equations. And the book says that it should be a maximization problem. This aspect is not really important. And different books and different people and different solver softwares will do it different ways. But we'll find out that it's a slight change in procedure to swap from a maximization to a minimization. But the book just wants to standardize on maximize. So that's why they call for that. So we've discussed how to do the second part. All of the non-negativity constraints are equations. And so we need to discuss quickly how to make sure that all of our variables are non-negative. Suppose we have a free x variable, and I'm going to use one of the constraints we had earlier. And I'm going to say that x is free. In other words, it's unrestricted, or it doesn't have a non-negativity constraint. And we've done this process before. If you remember, I talked about modeling absolute values as linear equations. We're going to do sort of the same process here. So we're going to define two new variables, x plus and x minus, which are greater than or equal to 0. And we're going to say that x is x plus minus x minus. This lets us express anything, any real number, as the difference of two non-negative real numbers. So if x equals 3, we get x plus equals 3, x minus equals 0. If x equals negative 5, we get x plus equals 0, x minus equals negative 5, positive 5 rather, because x minus needs to be non-negative, because we want all of our variables to be non-negative. Now you may notice that we could also have x plus equals 1 and x minus equals 6, and that would work. So this is not sort of the most robust constraint. It doesn't seem like it anyway. But as it turns out, this will never cause an issue in our LP. in our maximization problem. If you don't have an objective, it can give you some extraneous sort of solutions, but it's not an issue if we have x in the objective. So we rewrite our constraint 5x plus minus 5x minus plus 2y greater than or equal to 10, x plus, x minus, and y are all non-negative. And of course we've already seen how to add slack variables to this. Minus s1 equals 10 x plus x minus y s1 are all greater than or equal to 0. Excuse me, my keyboard is angry at me. That is bizarre. My drawing tools have decided to not function. Give me a second, let me reboot this program. What? It has just quit doing things. That is totally bizarre. It's stuck on the selection tool. This is not a problem I'm prepared to fix. There we go. Another reboot did it. Excellent. Let me get back on the PDF. And we're back in business. Greater than or equal to 0. So this is similar to modeling absolute value of something. So that is how we deal with free variables to put them in standard equality form. So now we're going to explore how basic solutions and extreme points and slack variables all work together to give us a coherent picture. So let's start. My notes have gone away. Yeah, let's start by picking a point on this plot. I'm going to start with just the origin. Now I know it's not feasible, and we're going to show you how we can see that from our solution. So we have x and y equal 0. So they're going to be our non-basic variables. So this is our basis. It's just S1, S2, S3, and S4. So we're left with this augmented matrix. And it's already in row-reduced echelon form. So we don't have to solve it necessarily. We just have the solution x, y, s1, s2, s3. X and y are 0, as we've already said. S1 is -6, S2 is -10, 3 is 4, and 4 is 10. So just to draw these on the plot here, S1 is 6, S2 is -6, nope, -10, and S1 should be -6. S3 is 4, and S4 is 10. Now, does anyone see why this solution is not feasible? What about these negative signs? Well, S is supposed to be non-negative, right? In fact, all of our variables in standard equality form are supposed to be non-negative. So if we ever get a solution that has a negative entry in it, that a basic solution, or any solution at all, that has a negative entry in it, it's not feasible. And we can see that graphically because our origin is not inside the feasible region. Now let me explain how I got this particular graph, or this particular matrix. I just said that I want a less than or equal to for all of my inequalities. So I subtracted, or I multiplied by -1. Minus 2y minus 10 for all of these. And then I added slack variables to each. And I wanted less than or equal to, so my slacks coefficients would be positive. So plus 1s. And then you can likely see that that row is the blue constraint. This row is the yellow. This one is the green. And the last one is the red constraint. So I just pulled the coefficients off, added an identity matrix for the slack variables, and then tacked on the right-hand side. So let's instead pick a... Let's start by picking a basis rather than picking a point on the graph. I'm going to arbitrarily pick the basis S1, X, Y, and S4. Now I've put these in a particular order just to make the solution process a little less frustrating. So I'm just going to grab the columns corresponding to my basis in the order that they're given. And then tack on the right-hand side. Oh, I missed a column. Zero, 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 one. Now I've put it in this order because we already have two entries for an identity matrix in their correct spot. So that solving this by row reduction has a few less steps. Now I'm not going to bore us by doing however many row operations. You should all be familiar with that process from linear algebra. So I'm just going to present the solved system. And we have 32/5, 2/5, 4, 66/5. And now we have a solution, but we have to interpret, we have to decide which variables take which values. So remember that we had our bases in this particular order. First column was S1, X, Y, and S4. So this translates to an identity matrix times S1, X, Y, S4 equals our right-hand side. But then an identity matrix times a vector just leaves the vector. So that is our solution that we get. If we wanted to put it sort of in order, x is 2/5, y is 4, so 1 is 32/5, S2 is 0, S3 is 0, and S4 is 66/5. Yeah, 66. So what solution does this correspond to? Well, or what point on the plot does it correspond to? Well, x and y are our two decision variables. They're the ones in the plot. So that's going to be x is 2/5, y is 4. That's this point. And we can see that it is the intersection of those two. It is exactly the intersection of those two hyperplanes, of those two constraints, because S2 and S3 are 0. S2, of course, corresponding to the yellow, and S4 corresponding to the green. What that means is that the sort of distance between our solution, our basic solution, and the hyperplane that is that constraint is 0. There is no distance between those two things. So our point is on that hyperplane, on both of those hyperplanes. In this case, we're in 2 dimensions, so they're lines. I'm not sure why I'm saying hyperplane so much. Other than the fact that this does generalize to n dimensions. Yeah. So, just as a reminder, S4 is sort of this distance. 66/5. And S1 is 32/5. So remember I said that extreme points are the intersection between n hyperplanes. If you're in an n-dimensional, if you have n decision variables. So that's what we have here. It's the intersection of 2 planes, 2 of our hyperplanes. And in fact, in the last problem, or the last slide, we had the origin, which was the intersection of 2 non-negativity constraints. So that is also valid. But in our problem here, it wasn't feasible. So not every basic solution is going to be feasible. Only the basic solutions that have positive values are feasible. And all of those feasible, every feasible basic solution is an extreme point. So that is that's sort of the most important piece of information here, is that if we have our, well, first, we can put our polyhedral feasible regions, we can define them as systems of linear equations. And basic solutions to those systems of linear equations, that are feasible, correspond to extreme points, and that extreme points are potential optimal solutions. So that is so today we have learned how to search for extreme points to LP feasible regions, which is a big important step. The next several lectures will be determining how to intelligently search all of these extreme points. Because as I mentioned, there could be as many as m choose n, which is upper bounded by m to the n. Many, many, many possible extreme points. So we don't want to look through all of them. We want to be intelligent in our searches, and that's what the simplex algorithm we're going to learn in the next few lectures and the next few readings is going to help us do. Yeah. I just wanted to, okay, so that is all the content that I have today. I wanted to reiterate that the reading order has changed slightly, so the schedule has been updated on the syllabus. Tomorrow's reading is a little bit long, so be prepared for that. Don't get bogged down in it. Skim it, get the big picture sort of ideas, take the reading quiz, and then we'll talk about it tomorrow. The project has been posted, so get some groups for that. I'll assign anyone who doesn't have a group by let's make it Thursday. So groups by Thursday would be ideal. Remember, we have to move quickly through this class, so we don't have our full a huge number of weeks to organize this and do our groups. So Thursday is the day that I want everyone to be in groups. Just email me your groups. I think that's everything I have to say. I'll stick around for questions.
So, Professor?
Sure.
You mean we choose the group by ourselves, right?
Yes. Anyone who is having difficulty doing that, I can assign some groups.
Okay. And one more question. So for this question, the basis is randomly choose or it's already set by the problem?
In this problem, I picked it arbitrarily.
Okay.
Well, I picked it
So,
because I knew it would line up with that particular point. But
but
yes,
if I gonna do the same question for that, so I just randomly choose or follow
if
the.
I'm giving you a problem like
Uh-huh.
this, I will give you the basis.
Okay, understood. Thank you.
All right. So everyone is free to go, but I'll stick around for a second. Hayden, did you have a question?